Well, good evening, and welcome to Kopernik Observatory. It's great to see you in here. It's great to have a nice packed house. My name is Drew Desker. I'm the director here at Kopernik, and it's great to see some familiar faces and a lot of some new faces. Just as a matter of interest, who is here for the first time? All right, mostly on that side. Okay. Didn't know there were. And then who here is a member? Ah, okay. So those people that raised their hand first, talk to the people who raised their hand second. Kopernik Observatory, we're a nonprofit, informal STEM education facility, and we belong to an organization called the ASCC, Association of Science and Technology Centers. It's a consortium of over 350 other science centers that honor each other's memberships. So a Kopernik membership, you buy a Kopernik membership here, you can take it to the center. Okay, I guess here we go. You can take it to the Ithaca Science Center, the Museum of Science and Technology up in Syracuse, the Franklin Institute, the Intrepid down in New York City. So there are 350 other science centers that you could get into using Kopernik's membership. So if that's something that if you like this kind of place, you may want to consider getting one of our memberships. So this is, in fact, we finally are kicking off our Friday night programs. Every Friday from March to mid-December, we'll offer a program of some sort. So tonight, in fact, is Motions of the Moon. Next week, actually, will be a BU professor that will talk about earthquakes. So, of course, he'll be talking about, how and why did the earthquake in Turkey, why was it so severe, and are there any ways that we can sort of predict how those kinds of things are going to happen? Also, as it turns out, this professor is doing some research right here at Kopernik. There are, on Kopernik property, he's got about 6 seismographs that he's studying seismic activity as it relates to fracking activity down in Pennsylvania. And so I'm sure he'll touch on that as well. The weekend after that, we've got a hot air balloon pilot that's going to talk about what's it like to be a hot air balloon pilot, a little bit of history of that. So every week it's going to be something different. And so check out our website. And the other thing also is, if you can't make an evening program up here, we always live stream our programs, and so you can go to our YouTube channel and pick that up. But also, even if you miss it live, you could watch it as a recorded program. So Kopernik does a lot of things. We do these public programs. We do a lot of school outreach. We have a very extensive STEM-based summer camps that we'll be announcing those in the next couple of days. We're doing a program during the school break in April called Girl Power, and we're really trying to promote more women in STEM careers. The theme for this particular Girl Power is called She Rose, and actually, I had to look it up. I'd never heard of that term before, but turns out that term is actually over 100 years old, and it's really promoting women that have done extraordinary things. And so we still have some openings in that camp. So Friday nights, again, we always do some sort of a program here. Then we invite you afterwards to come out and take a look through our scopes at the night skies. Even people who live here in the area will come up here and they'll look on a clear night. They're like, "Where did all these stars come from?" And you need to come here to do that. One of the things that we do, however, is when you get sort of a night like tonight where we're not going to be able to do any of that thing, if you paid for your admission, you can go back to the cash register and we'll give you a complimentary card to come back. If you're a member, you can get it anyway, so you don't need that. But anyway, we're very fortunate this evening to start off our spring or our 2023 Friday night programs with Peter Klimas. Peter has done a number of programs up here, and he's a physics teacher for the Vestal School District, but the way he presents the information is just really engaging, really exciting. You're really in for a treat. And so, Mr. Klimas.
Thank you very much.
The floor is yours.
Thank you. Hey, happy St. Patrick's Day, everyone. Thank you for being here tonight, and thank you to all the people that are watching online live. This is great. I'm excited to get going. I've got a lot of stuff going on, but when I think about presenting up here at Kopernik, I never know who my audience is going to be. I never know if you're going to know a little bit or nothing at all or a lot of it, and so I like to start at the beginning, but also treat everybody as if you're going to come along with me the whole time. You're an intelligent audience, and so I could go as far as we can possibly go. So let's get started here with the motions of the moon. When I thought about this, I wanted to divide it up into 7 parts tonight. All right, 7 parts. And I'm going to start with the real basics, which is the phases. Let's learn the phases. Let's do that together. But after that, then let's look at 3 different points of view. So let's take a look at the sun and the earth and the moon system from the point of view of, I call it space, space's point of view. Then let's come down here onto the earth and see what it looks like from our point of view, the horizon, outside point of view. And then finally, from the moon's point of view, a little bonus for you. All right, so those are the first 4 parts. 5, 6, and 7 then go together. We're back in the Earth's point of view. So now back on the Earth, let's review a little bit about what the sun does every year. And then we can talk about what the moon does that you may or may not know every month, having a little bit, like getting more advanced here, past those stages. And then finally, this fancy thing called the major and the minor lunar standstills, which we're actually coming up on in January of 2025 will be the peak of the cycle, but we can already observe this today. All right, and I'll even show you some of the data from coming right up. So the phases. I like to use a picture to illustrate, right, what we want to learn. And if you understand everything in that picture, that's it. That's this first part, right? Do you know all your phases of the moon? If you do, great. Let's just do maybe a little bit more about each. All right, so here's just some drawings of the exact same thing. And, you know, we got the names. Typically, we start the cycle when we can't see the moon. You could start a cycle anywhere because it's cyclical and it goes around and around. But, you know, the beginning of the cycle is typically new when the moon is not visible. But soon enough, we see this waxing crescent, first quarter. Now, the first quarter, that gets sometimes people, it's a half moon. But that's like right? The astronomy people are like, well, it's actually a quarter moon. But a half moon is a great description of it because it's half illuminated, but it's a quarter of the way through the cycle. All right, then we get to this waxing gibbous. You can see it. Eventually the full moon. And then the moon starts to die down again, waning gibbous, last quarter. You're like, it's not a quarter, it's a half. You're like, but it's the last quarter or it's the third quarter in the cycle, waning crescent, and you're back to the beginning. All right, did you get all that? Like if you already knew it, sure, but if you didn't, let's do a little bit more. So this thing, right, it starts with a full moon, but typically we don't start. You ready to, I like to, that audience participation. Are you ready to say it? What kind of moon? Let's say it together. New moon. And then we're going to see a
waxing gibbous.
Waxing crescent, and it was halfway, that's a first quarter. Now it's a waxing gibbous, and finally a
Full moon.
ooh, now we're in the waning gibbous. We're going to a
Last quarter.
last quarter, and a waning crescent, and then we're back to the beginning. And that whole cycle, right? That cycle from new moon to new moon takes, for the elite, 29 and a half days. All right, 29 and a half days for the full cycle of phases, like a month. All right, so, you know, one of those words in there was a crescent phase, and I've got the 2 crescents. And a crescent phase, I looked up these definitions, and then I picked the definitions that I liked. But it's a curved sickle shape, right, of the waxing or the waning moon. So it's basically like self-defining, right? The crescent moon is the shape of the crescent moon. But it's also, right, a thing that's got a shape. It's like a curve, and it's broader in the center, and it tapers to a point at each end, like a crescent wrench or a crescent roll. Yeah, you see those crescents right there, right? The crescents, yeah. All right, then there was the other descriptive word of moons is gibbous. And gibbous is, right, marked by convexity or swelling. The moon, oh yeah, like a gibbous moon, like it's, the one that's the gibbous one. That's what gibbous means. But it's a moon that has more than half, but not all of it is illuminated. And then also humpbacked is this meaning of the gibbous. Check this out, ready? Ooh, that gibbous shape, there it is, right? That's the gibbous. That shape it's not a circle, but it's more than half. All right, and then to wax. To wax is to increase in size, in numbers, strength, prosperity, intensity, to grow in volume, to grow toward full development, to increase in phase, like the moon, and to become is that last definition. That moon is becoming full. It's waxing. Now, I had the pleasure of reading The Merry Adventures of Robin Hood by Howard Pyle recently, and the language is like this old English style that I had to get used to for a while, but he used this language like, when the four yeomen had traveled for a long time toward Sherwood again, high noontide being past, they began to wax hungry. Right? They were growing hungry. It was getting late, and they hadn't eaten, and they needed to eat. And there was this great fight between Little John and the cook. Then fetch it hither, cried Little John, who waxed angry by this time. Right? And I guess if you wax hungry and you wax angry, you wax hangry. Oh. I used the phrase, right, wax your knowledge of the motions of the moon, right, in the description of this, to mean increase, right, to grow, to increase that knowledge. All right, and then lastly, there's the word wane, and we have these two waning moons up top. But to wane is the opposite of to wax, to decrease in size, to dwindle, to diminish, like the moon or other satellites, and to become less brilliant, to dim, to flow out and ebb away, to fall gradually from power, prosperity, or influence. And again, a quote from my reading of The Merry Adventures of Robin Hood, then forward, quoth Robin, for the day wanes, and it will be dark ere we reach Newark. So the moon can wane, but the day can wane, right? And we can wane if we get, sickly. We could look wane. What kind of moon? So that's last quarter? You guys are like freaking me out. That's the last quarter, the third quarter for us here in the Northern Hemisphere. It's illuminated on the left-hand side. Let's go back a second. Hold on a second here. Let's point something out. Take a look at that edge between the light and the dark. If I could grab it, I could pull it from the right side of the moon across to the left side of the moon. That edge between the light and the dark on the moon is called the terminator. And the terminator pulls from the right to the left. And so the shade, now I'm grabbing the darkness and I'm pulling that shade across the full moon until it's all new. And then when it's a new moon, I'm going to grab that shade on the right-hand side again and I'm going to pull it across the moon, pull, 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 pull. The terminator moves from the right to the left in the Northern Hemisphere. Yeah, and that so if you step over the line, right, it flips over. That freaked me out for a while. Yeah, exactly, right? So, but I think what happens is, and we see moons that are often, right, kind of like, maybe like here is the crescent, right? Or where is that crescent, right? Is it more toward the bottom? And I think that as you kind of move south and south and south, you start to flip up the moon. Instead of right to left, it flips up. And then eventually it starts flipping the left-hand side, right? So there's a gradual process as you move into the southern hemisphere. But this moon would be a third quarter, last quarter, because you're going to pull that shade and it's going to dim more, and that's the last quarter. The first quarter would be illuminated on the other side. Another quiz. What kind of moon? That's a waxing gibbous, because that shade is going to pull. It's going to get more light. It's going to become full. It's waxing. And then lastly, what about this one? That's a waning crescent, because you're going to pull that shade and that darkness is going to go across and it's going to wane away. All right? Yeah. Part 2, we got the phases. Part 2. All right, so I like to call this is the spaces point of view, because we got to zoom out here, and then if we understand this diagram, we understand everything about this second part of the talk tonight. All right, part 2. Why do we have phases of the moon? Well, when I was a little kid, I remember being told it was the shadow of the Earth on the moon. That's totally wrong. All right, why do we have the phases of the moon? Because of the, it's because of the geometry of the Earth and the moon and the sun system. That's why, right? It's where we're looking from our point of view on the Earth is why we get these phases. And there's a great diagram that explains it all. Let's get into that diagram a little bit. This is from the Jet Propulsion Lab, NASA's, and it's just a great little demo here of how the phases of the moon work in a model. Where is the light coming from? The left, thank you. Yeah, the left. And what is that styrofoam ball?
The moon.
The moon. And what is that woman's head? The Earth, right? So there's the model. And so looking from the point of view of the Earth, you see different phases of the moon because of the way that the light is shining on it. But the whole time, the light is coming from the left. There it is. The light is coming from the left. But what you see would be you wouldn't see it, right? It would be dark, and you couldn't see it. But as that moon moves off to the side, now that sun is still shining on the moon. It's still illuminating 50% of the moon, but you start to get a little sneak peek at some of that light coming on the right-hand side. Now, as you go into the next position, now that light is shining, but when you look at it, you're seeing half and half. And the half that you see is on your right-hand side. You're like, no, it's on the left. No, from this point of view, it's on the right-hand side, from the Earth's point of view. You keep going, and you've got wait, what kind of moon is that? Oh, waxing gibbous, it says it. And then you get to the full moon. Now, this isn't if you block it with your head, right? That would be an eclipse. But if you don't block it with your head, which normally happens, the full moon happens far more often than an eclipse, you get the light shining on the moon and you see a full moon. Now it starts to wane, and that little darkness, from the point of view of the person, there's that little darkness that you're getting a sneak peek at. You get to see half the darkness, you get to see most of the darkness, and you get to see all the darkness back to the beginning. All right, so back to this diagram, right? That was the diagram acted out, but let's focus in here in the middle of the diagram first, all right? So we saw the diagram, we saw it acted out, but what about here in the middle, the Earth part of the diagram? All right, so now I want to show you something that I did to you on purpose. You see where the sunlight is coming from in the diagram, the main diagram here? From the right. But then what did I just do? I switched the sunlight up to the top, right? Can you handle it? Can you handle just turning the page around and looking at it from a different point of view? Now look at that Earth. That's normally not how we draw maps of the Earth, but that is the Earth. Who lives right there? Does anybody know? Santa Claus is right. That is exactly right. So we're looking at a weird view of the Earth where the middle of the Earth there is the North Pole. We're looking at you ready for it? Top view of the Earth. Who's to say that that's the top view? But that's the top view, okay? That's the top of the world, and we're looking down on Santa's house. That's the way that this diagram works. Now, you might not realize that from this picture, all right? But that's what we're looking at. We're looking at Santa's house. All right, where is the day and the night? Well, if I could say, where is the day, maybe you would say the northern hemisphere. No. Where, in this picture, right, where is the day? The day is on the top half, which would be both northern and southern hemisphere. Now, we're only looking at the northern hemisphere. We're looking at, do you see this? What is this right here? Ooh, that's the United States. Do you see that? That's the United States right there. But around that would be the southern hemisphere. There's South America down there that's also getting light shining on it. Where is the day and the night? Well, the light would be where the sun is shining, and then the other side of the Earth would be the night, where the sun can't shine. All right, did you know that if it's 8 o'clock here in New York, like this talk started at 8 o'clock, then what time is it in California? Do you know this?
11 p.m.
5 o'clock is the correct answer, all right? 5 o'clock. California is 3 hours behind, right? 3 hours behind, 5 o'clock p.m., 8 o'clock here. So, 5 o'clock. Which way, then, is the Earth rotating? Right, this is our observational evidence. You know that it's behind in California, right? Wait. Where is California?
Over there.
Is it like on this side, or is it like on that side?
That side.
Ooh, there's like California, yeah? So like, am I going to turn California into the night, or am I going to turn the East Coast into the night? Turn the East Coast into the night. And so we're rotating, counterclockwise from a top view, the Earth rotates. Okay. All right. So then we're going to oversimplify here because, right, the world is far more complicated than whatever you learn, it's more complicated. That's what I've learned as a physics teacher. Whenever I think I understand something, you're like, oh, yeah, but then it's like actually more complicated. So let's oversimplify and just do like an equinox day, all right? Like just a nice easy day, equinox. Not like now, like we're actually really close to the equinox, but we did this time change. It's like forget about all that stuff. All right, where would like 6 a.m. be, right? On this picture, where is 6 o'clock in the morning? Well, 6 o'clock in the morning is kind of like when the sun rises, let's just say, right? For easy numbers here. And that would be where you're turning from the night into the day. Yeah, 6 o'clock a.m.? And if you kept turning, where's 12 o'clock? Well, 12 o'clock is when the sun is over your head, shining down on you. And then if we keep turning, we turn into the night. Yeah, 6 o'clock p.m., that's right.
That's 12 p.m.
That's 12 p.m., that's right. I'm pretty sure.
No.
and then we get to 6 o'clock p.m., that's like nighttime, the sun is setting. And eventually we get to 12 a.m., like also called midnight, in the middle of the night. Yeah. So that's all on the diagram, but you can't see it, but it's there. What time is it?
6 o'clock.
6 o'clock.
A.m.
I moved the sunlight again on you, yeah? It would be 6 o'clock p.m. Because you would be turning into the night. I didn't draw the night this time, did I? No, I didn't draw it. But you'd be turning into the night, and that would be at that edge between where the sun is shining and you're turning into the night. I decided to put that little person in Africa. You see that right there? That's Africa. All right. If I had the person stand here, it would look like they were standing in the ocean or something. Yeah, do you see that? Okay. What time is it? 9 p.m. I like it. 9 p.m. Good job. And again, I'm oversimplifying because we're just saying that, hey, you're going to turn counterclockwise, and as you turn from the light into the night, that would be about 6 o'clock p.m. And then over here would be midnight in the middle of the night. So in between 6 and 12 would be like, how about 9 o'clock p.m.? Okay, good. So that's the Earth part of the diagram. Let's look over here. Those are the moons. Only 3 of them, though. All right? Oh, wait, there's only 1 moon. No. But like 3 phases of the moon. All right, so first, let's shade in the dark side of the Earth and the moon. Well, we just did this. If we got the light now coming from the right, then we're going to have the right side's light, and we'll shade in the left side's dark. Okay? Good so far? Let's divide the moon. Now, we already divided the moon in light and dark, but let's divide the moon again into the side that we can see and the side that we cannot see. Now, the lines that I'm about to draw for you have a name, a special mathematical name, with respect to that orbit of the moon. They're tangent lines. Ooh, yeah, nice. And so this is going to cut the moon now from the side that is facing the Earth from the side that is not facing the Earth. And so now, what do those moons look like from the point of view of the Earth? Well, the middle one, I think, is the easiest one, because from the point of view of the Earth, the middle one would look like a, oh, good job using your words, a new moon. Like all dark, right? All dark like a new moon. Let's go up to the top one. The top one, when you look from the point of view of the Earth, you would see, you see like a little pie slice on the right. Yeah, you see that light pie, that's on the right side. That's a waxing crescent. And then what about the one on the bottom? Again, you got to put yourself in the point of view and look and say that sliver is on the left. That's a waning crescent. There it is, waning crescent. Good? Which way is the moon revolving around the Earth? Do you know your order of the phases? Which one comes first, and then which one comes after that, and then which one comes after that? Just shout it. I like the shouting out here. This counterclockwise. Yeah? It would go like waning crescent, and you'd pull that terminator so that the shade would be all dark, and then you'd pull that terminator from the right, and you would get a little sliver of right coming on. It would be counterclockwise. So the Earth is rotating counterclockwise, and the moon is orbiting counterclockwise. Okay. So then we could play that same game with all the other moons. The first thing that I did was I sliced them in half, light and dark, already done. Then what I did was I sliced them in half. The side that we can see from the side that we cannot see, I drew the the tangent lines. All right. And then, so you got to put yourself on the Earth. And then you look up at that top moon and you say, hey, that moon up above has got light on the right and darkness on the left. That's a first quarter moon, see? And then I look up at the next moon in order, and you're like, ooh, waxing gibbous. Ooh, look, it's all light. Ooh, look. It's got a sliver of darkness on the right. Now, this is my favorite one. Because you're like, no, look, the light is on the right and the darkness is on the left. No, the light is on the left, the darkness is on the right. But from the point of view of the Earth looking at that moon, my right hand, the darkness is on the right. And there's the phases of the moon. From the diagram, like this is why there's phases. It's not because of the shadow of the Earth. That's an eclipse. It's because the Earth is going around and we're seeing different parts of the side that the sun is shining on it. Okay. Right? Did you think you understood? This is my favorite question to ask and then say, don't answer that, right? If you think you understood, then tell me what the phase is.
Waxing gibbous, and also that looks like a hydrogen atom.
Yeah, it kind of does. The blue thing is the Earth, and the gray thing is the, and then the sunlight's shining on it. So wait, what was that phase?
Waxing gibbous.
I'm not feeling like a confidence yet. A waxing. Whoa. Mr. Climus, what did you do there?
Waxing
Okay,
crescent.
I put up a lot of answers, but this one's in my head. That's a waxing crescent. That's a waxing crescent. Now, the way that I do it is actually not the way that I showed you, by the way. Right? The expert does something different than the beginner. I showed you the beginner's way to like slice them, and like that's how you do it. But what I do is, what's this moon right there where the sunlight's shining on the back of it? New moon. Which way does the moon go? Counterclockwise. So from a new moon, that's the one after the new moon, which is a waxing crescent. Okay, that's the right answer. So what kind of moon is this?
Full moon.
That's a full moon. That's an easy one. Yeah, that's a full moon. And then what about this one?
Waning.
A waning gibbous. I would put that new moon in my imagination in between the Earth and the sun rays, and I go counterclockwise. Half would be the full moon, and I go one notch past the half, and I'd get a waning gibbous moon. Okay. What about this one? Oh, it's on a diagonal. Last quarter. I like to call it third quarter, but last quarter and third quarter, they're both good ways to call it. Last quarter, third quarter. All right? That's a quarter of the way around, 3/4 of the way around back to that new moon. Okay, good. Part 2. We did it. Part 3. Here we go. All right, part 3. So what does this all look like, though, from the Earth's point of view? Because you don't get to zoom out in space and look down on the Earth and the moon system and decide on like what the phase is. What you do is you go outside and you're on the Earth. And we're going to all be on the Earth, I think, for our whole life. All right. So we want to understand this diagram that I've got right here, and so I want to develop this diagram. This is a great picture, right? But let me develop that picture a little bit for you. Let's go back to the one that we now, understand. One problem with that diagram, it's a great diagram, right? But diagrams have their flaws. They're not reality. And one problem with the diagram is that the Earth is too dang big. And it's not gonna help me out when I'm trying to explain this. So the one thing to know is that the distance from the Earth to the moon, it's about 60 times farther away than the radius of the Earth. So I'm gonna shrink that Earth down, all right? Let's do that. And now you're like, oh, now the moons are too big. But whatever, okay, let's leave them alone. The Earth is bigger than the moon, but not in this picture anymore, but at least I made the Earth smaller. All right, next, let's put a person on the Earth, and this person, remember, that middle of the Earth is the Santa's house. And so this person is, around the side of the Earth, and I made the person giant. And I drew the person's horizon, but what time is it there? That's 6 p.m., good. Okay, that's 6 p.m. See, you're learning. This is good. I like this participation. Now, which way does the Earth rotate from a North Pole view? Counterclockwise. So watch this. Whoa! Right? A little bit went by. So from here to like here, this is a tricky one. What time is it now? So to like there. I heard the correct answer. 7:30. Now, this is in my opinion, okay? This is my opinion, because if you took that person and you rotated it all the way to midnight, then from 6 to midnight would be 6 hours, and I would argue that's like a quarter of a way to midnight. Would you agree with that? Like I went like halfway up to that waxing crescent, then the waxing crescent would be like halfway if I turn that horizon all the way into the midnight position where the person is on the opposite side. So I said, all right, that's like a quarter of 6 hours, which is like an hour and a half, and like, okay, fine. If this is 6, then that's 7:30. All right. Now, look at what just happened though. Let's say that there was a full moon, okay? From 6 to 7:30, what just happened to that full moon? It just rose up into the sky. Do you see that? And what about that new moon? No, you can't see new moons. Waxing crescent moon. You could see a beautiful waxing crescent moon there, right? And then when we go from 6 to 7:30, what just happened to that waxing crescent moon? It was setting. Do you see how it's setting right there? So this is, I think, very counterintuitive, but the side that is rising is the setting side. Yeah? Whoa, yeah, right? Like I rose that horizon up because we rotated around counterclockwise, and the side that is moving down is the rising side, right? Does that make sense? Did I confuse you? I like to try to teach you really well and then also confuse you a little bit to make sure that you're on your toes. All right, so this is the big idea that I was just showing you. And so now let's go back to this. Okay, so we already said it was 6 p.m., but at 6 p.m. then, if you're standing in that spot on the Earth, look along the ground, and what do you see? The sun over there, and the sun over there was on the setting side. Yeah? The setting side was the sun. Boom, let's put that sun in. The sun sets in the west, didn't you already know that? But the sun is on the setting side. And then, guess what's really close to the sun? If I look in the direction of the sun, that's also in the direction of the new moon from that diagram. Now, if I go up into my sky, what's that first moon that I would encounter in the western sky, but not all the way up? That would be that waxing crescent moon. You see it there? You see how I'm making the one diagram the other diagram? And then above my head would be a first quarter moon. And then over on the rising side, yeah? The rising side now, that's like the things rise in the east, certain as the sun rises in the east. That was from Beauty and the Beast. Then you've got the waxing gibbous there, and then down on the horizon at the sunset, the full moon rises when the sun sets. Did you know that? And so there's that same diagram. Now, we can also play the same game and just keep going, and this might seem weird, but it's like there's an underneath the Earth. And the Egyptians really got into this, right? You go underneath and around and back to the other side. But there is the waning gibbous. Now, I dimmed it a little bit for you. Do you see how I dimmed it? Because that's like underneath the ground. And then all the way on the other side of the Earth would be the last quarter moon. and then coming around would be that waning crescent, and then we're back to the new moon. And one thing that confuses people about that diagram is that I chopped it into eighths. But sometimes people don't feel like it's eighths because it's like 3D and 2D. Does that make sense? I flattened a 3D thing, and so you're like, no, but look at all this space right here, and look at how close these are. These aren't in eighths. Yeah, but they are in eighths in 3D. Yeah. Okay. Now, you could play the same game and just move the sun. Instead of having the sun setting, you could have the sun rising. And you could say, hey, right where the sun was the new moon. And then what I'm going to do is I'm going to work myself backwards from the sun. Now, why I say backwards? Because on a daily basis, on a diurnal basis, the sun rises in the east and sets in the west. That's like the motion of all the stuff in the sky. But over the course of the month, you got to work those moons back. And so you say, hey, there's the new moon, there's the waxing crescent moon, I'm going to work it back, there's the first quarter, work it back, there's the waxing gibbous, there's my full moon opposite the sun, work it back, there's my waning gibbous, third quarter, waning crescent, and I'm back to that new moon. I work my way backward around the circle, backward from the point of view of the daily motion. Yeah? Yes. Whoa, I broke this. What time is it?
It's 12.
Hold on. I feel like I broke my clicker. I got it. Kind of works. All right. What time is it? Time is like 12 o'clock p.m. Noon. Yeah, noon? What kind of moon is that? It's a smiley face because I didn't tell you, right? What kind of moon would that be? So the debate would be first quarter or last quarter. And you got to work your way backwards around the circle. So backward would be to start at the sun and work your way back to the east, all the way around to that moon, 3/4 of the way around the circle backwards. That is a last quarter moon. Last quarter moon. That's the right answer. Okay, same game. What time is it now?
It's
6 o'clock p.m. The sun is setting. What kind of moon is that?
That is a waxing crescent. Waxing crescent.
Working my way backward from west would be to go back to the east. That's like one notch back to the east. I'd call that a waxing crescent moon. That's a I know it is. I just let other people think too. Okay. What time is it at, when the sun's rising in the east? Maybe, let's say, 6 o'clock in the morning a.m. And then that moon would be, hey, kid over there, give other people time to think. You would work your way all the way around that circle, going backwards from east, and that would be a waning crescent moon. Okay, you got that game? I got another game. It's the same game, but I'm just going to mix up it a little bit. What about a third quarter moon at 6 a.m.? Well, where would the sun be at 6 a.m.? You'd put it in the, you can picture it? Boom, there it is. So where would the third quarter moon be? A third quarter moon at 6 a.m. would be, you got a prediction in your head? On the top. A first quarter moon would be down at the bottom. That would be backward from east, would be right in that kind of like midnight position, if you will, at the bottom. That'd be first quarter moon, but third quarter moon would be up there. All right, what about a full moon at 3 a.m.? First off, where would the sun be at 3 a.m. on this picture? Well, 3 a.m., that's like for really early risers or people that like stay up really late. And so that's after the midnight position, and the sun rises in the east, and so there's that sun in the 3 a.m. position. I kind of dimmed it. It's underneath the ground in that position. But where the heck would a full moon be? Well, a full moon would be opposite the sun. It would be, halfway up in the western sky. There would be your full moon at 3 a.m. All right. So one of the advertisements for this was tell time at night by the moon. And you know, you can't get down to the minute or anything like that, but you could get ish kind of what it is. And so here's the tell time at night by the moon. It's night. And there's a waning gibbous moon right there. You know, kind of plus or minus an hour, depending on the time changes and, you know, if we're really kind of like an equinox day or if we're like in the midsummer or midwinter kind of thing. What time would it be? So you've now got to figure out where the sun is so that you can work your way around the circle backwards from west to east. And you can go through new moon where the sun is going to be, where you want to put it. Wherever you think that sun is, that's where you're going to put that new moon. And then one notch back is the waxing crescent, first quarter, waxing gibbous, full moon. There's your waning gibbous right there. So the time would be, you know, 12 a.m. Yeah, in the middle of the night. That would be in the middle of the night right there. That's it. See? All right, it's the night, and there's a full moon. It's risen up from the east. It's not as high as it could be in the sky yet, but it's there in the eastern sky, maybe about halfway up. You know, what time is it? 9 p.m. Opposite, right? There it is, 9 p.m. Nice. All right. A favorite book? Reading to kids? Good Night Gorilla. Good Night Gorilla. And then when you know what I've shown you about the moon, you just are bothered by this Good Night Gorilla book. What time is it? Dang it, it's hard. I didn't give you that damn diagram. So a waning gibbous here, excuse me, I said gibbous. A waning crescent here. You see a waning crescent in the sky. Now look at the sky. Doesn't it kind of look dark? It kind of looks dark, so we got to go with that. All right, it's kind of dark out. And we got a waning crescent. And the waning crescent moon you're going to see right before the sun comes up. Good Night Gorilla. Are you kidding me? The sun's about to come up. This girl's been up all night or something. They should have put a waxing crescent moon in there, not a waning crescent moon. They got the moons wrong. All right, I wrote this poem. The sun sets before the moon. A waxing crescent will be full soon. The moon rises before the sun. The moon's cycle is almost done. All right. Oh, thank you. Oh, but it's just a nice way. If it's sunset, you're going to see a waxing crescent. But if you get up really early in the morning before the sun rises, you could see a waning crescent, provided that that's the phase of the moon. It could be a full moon, and you won't see either one. But if it's a crescent moon, that's when you're going to see it. Okay. I've got these handouts that you're welcome to take today. All that stuff that I've explained so far, this is again from the Jet Propulsion Lab. I just made copies for everybody. You could build yourself like a little moon calculator and when the rises and the sets are, but I already taught you all that, so you really don't need a calculator, right? That's for dummies. I'm just kidding. That's like a nice tool that you could use, but all the stuff that I explained, that's in that tool. I've got those copies if you so desire. All right, now, I knew that I had way too much tonight, and I'm really feeling like we still got time, but how far are we going to get tonight? We'll see. Part 4. What about if we went to the moon's point of view? I like this one. This is like a real great bonus round. All right, now I want to go back to this picture. I already showed this to you. This would be a visualization of the phases of the moon, and this is from the Earth's point of view, by the way. All right, by the way, we're looking at the moon from the Earth, and that's why we're seeing the phases, because we're looking from the Earth. And as the phases change, one thing you may notice is that there is a little wiggle here, okay? But like apart from that little wiggle, we are always looking at the same side of the moon. There's a rabbit in the moon there. The rabbit's ears are kind of flopping down on the right-hand side. They're in darkness right now. We're going to get to see it. The ears are going to come on first. Then the head of the rabbit. That's at least what I see. Okay, so there's the ears. There's the head of the rabbit. And then the body of the rabbit drops down on the left-hand side. You kind of see that rabbit? And we always see the rabbit, all right? We always see that side of the moon. And so does the moon rotate? Well, yeah, from the point of view of the Earth, I say no, okay? From the point of view of the Earth, we always see the same side of the moon. We do not see it spinning around. We always see it facing us. And that's going to, like, agitate people that know about astronomy. Okay, so right, because it's going around, right? But I would just say, from the point of view, I told you it's going to agitate people that know about astronomy, that from the point of view of the Earth, it's not rotating. We're looking at the same side. But you see, from the space point of view, which was this diagram, that was the space's point of view, I put a little person on the moon. And that person on the moon maybe is standing in that dark area that's the head of the rabbit, okay? And that dark area that's the head of the rabbit is always facing the Earth. So that person is always facing the Earth. And then if you go from the 1 and you go counterclockwise, you say, oh, look, that person is rotating around. And so from the space point of view, is the moon rotating? Well, definitely yes, right? Yes, the moon is rotating from that point of view. It's turning around. The moon rotates once every 27.3 days, and this is called the sidereal period of the moon. That's with respect to the stars. And this gets a little bit fancy here, but I think I can act it out. I'm the Earth. My fist is the moon. From a top view, we're going to go counterclockwise. And the thing is, though, that, see, the Earth also moves around the sun, which is like in the middle of the room here. And so I, the Earth, am also moving. Oh, look, the moon just got all the way around 27.3 days. But to line back up with the sun, it's got to go a little bit extra, 29.5 days, the time that it takes from new moon to new moon, the time of the phases. So we got this little fanciness because we got a lot of things going on. All right. But the title of the section here was From the Moon's Point of View. So I just said from the Earth's point of view, we see the same side. From the space point of view, you can see that the moon is turning around once every 27.3 days. But what about from the moon's point of view? What would the sun be doing in the sky? So think about being that little person right there, right? What would the sun be doing for you as a moon astronomer? A lunar day is really long. The sun would be rising and setting. There would be days, but it would take 29.5 Earth days for one moon day. Yeah. All right. Now, from the point of view of the moon, what would the Earth be doing in the sky? Three things. I got 3 observations that you could make about the Earth from the moon. I like this first observation. What would the Earth be doing in the sky? Not much. It would not be moving much. You know that little wiggle that we looked at? There's a little wiggle, okay? There's a little wiggle, but not much. It would just be sitting there in the sky. There's something that sits there in the sky for us here on the Earth, by the way. What just sits there in the sky? Well, the sun rises and sets. The sun is moving through the sky. What sits there in the same spot in the sky for us on the Earth? Polaris does, the North Star, all right? But from the moon's point of view, the Earth would be doing that same sort of sitting there in the sky. 2 more observations about the moon, about the Earth from the moon. It would be going through phases. And when it's a new moon, it's a full Earth. And when it's a waxing crescent moon, it's a There's a little sliver of darkness on the right-hand side.
So it's
A waning gibbous Earth. I'll say it, yeah. When it's a first quarter moon, it's a last quarter Earth. Did I get the order right here? Yes! I knew what you guys were going to say before you said it, see? And then there's a third one. See, we got them in order. Good job. There's a third observation about the Earth that you could make from the moon. You would see that the Earth would be like an eye in the sky just sitting there. It would be going through phases, and it would be spinning. It would be rotating. You would see the continents go by. You would see North America, and then you would see Asia, and you would see all the different continents. It wouldn't just be the same picture of the rabbit like we see of the moon. It would be getting to see all sides. Nice. That was the bonus round. All right. So now we've got these extra parts, and I'm like, how late do you want to stay tonight? Well, I'll keep going. I think we still got. I'm planning on 10 more minutes at least for this hour, right? But let's see how we do. Okay, so good point. If you weren't that guy that I put, you could be on the other side. If you were on the far side of the moon, you wouldn't ever see the Earth. You would just be on the other far side of the moon. Just like we never get to see the far side of the moon, if you were there, you would never get to see the Earth. Good point. All right. So, quick review here, quick review.
What about the Apollo astronauts when they were, Michael Collins, when he was in orbit around the moon, he saw it rise and set?
Because he was in orbit about the moon. Right. Yeah. He wasn't on the moon, right? And so that famous Earthrise picture was taken from a spacecraft as it was orbiting the moon, not on the moon. Ooh, phases. It's got phases, see? Yeah. I already showed you, see? Okay, quick review here. Quick review. You know, the sun does this every year. Did you know this? This is it. This is the picture that I want you to understand in part 5. The sun does this every year. The sun changes where it rises and sets, and it gets higher in the sky and it gets lower in the sky, and this gives us the seasons, and it's because the Earth is tilted. Got it? There you go, part 5. Okay, I could develop that a little bit. Now, first off, did you see that this picture is actually backwards from the other picture that we were using? So I flipped it around. This was a great drawing that I found, but I was like, dang, it's backwards from all those other drawings that I had. So I could just flip it around like that, and then that would match it, and maybe we'd like it better or something. Plus, it's going to also match this one. So here would be summer solstice. The sun does not always rise directly in the east, but it always rises east-ish, so in the northeast. And it arcs really high in the sky, and on the summer solstice, it's as high as it's going to get, and it sets in the northwest. Now, as we move to the equinoxes, which we're really close to one right now, March the 20th, in just, 3 more days, is going to officially be the vernal equinox, the first day of spring coming up. We're really close. The sun is really going to rise pretty much due east and set due west. It's going to be a little lower in the sky. And then in the wintertime, the sun is the lowest in the sky, and it's actually rising in the southeast, and it's setting in the southwest. Okay. Now, we could get fancy, and we could do this little azimuth thing. And azimuth is just a way of telling which way you're pointing on the horizon. And so by definitions, because people decided before I was born, that north is 0 degrees, and then what you do is you go to the east. And if you notice, I flipped this thing on the side, because then it would match my other picture like this. You see how north was over on the left-hand side, and south was on the right-hand side? So I turned the wheel. You're like, why'd you turn the wheel? So that it matches the other ones. And so, okay, north is 0, and then we're going to go degrees around and be real specific, and 90 would be east. And that's because astronomy said so, all right? It's the way it is. All right, now, for us here at 42 degrees, here are the sun rises and sets at the extremes, and right in the middle in those seasonally important dates, all right? And you really can notice this if you pay attention to the rising and the setting sun, right? At my house, I actually don't get a good view of rising, but I get a great view of setting, and I really can watch that sun move across the horizon and back across the horizon as the seasons progress. And there's 65 degrees in between the extremes, by the way, for us. And you know why? Because the Earth is tilted, and let's just acknowledge that and not get into it and go to the next section. All right? What do you need to take away? The sun's rise and set positions, they move across the horizon over the course of a year. Sure they do, yeah?
But that diagram is for where we live.
That one's for where we live.
Go. Yeah.
Sorry, I'm still not sure.
This diagram is very vague-ish for where we live. It's like about-ish where we live, sure, right? I tried to be more specific right here, okay? This is vague but true. Oh, okay, you like that? Yeah. All right, now, the moon, it turns out, does the same thing. Except the moon only takes a month to go around the Earth, and so does that whole cycle in a month. Did you ever notice that? It's harder to notice. It's much harder to notice because the sun shines in your eyes at certain times of the month, and you know, you don't have good view, and then, I don't know. All right, so let's develop that a little bit. These are pictures taken from Stellarium. So this is coming up on the date of the next new moon, which is March the 21st. All right, on March the 21st, which is in 17, 18, 19, 20, 20, 4 days from now, that's going to be a new moon, officially. And if you can't see the new moon, it's right there. Okay, it's right in those little crosshairs. I clicked on it. And these are approximations here. Okay, I'm not trying to be super exacting, but I'm using this program called Stellarium to get a read on, look, the new moon is right in the same spot in the sky as the sun. And look, the new moon is rising at 7:25 in the morning, kind of like the 6 a.m. time that I gave you, but you know, we all just sprung forward, so. Now, look at that azimuth. There's 95 up at the top. It's in between 95 and 100. I call that 97. All right, let's give it a 97 right there. All right, 97 is the azimuth of the rise, and I put a big fat moon, and I kind of centered it in 97. Okay? Ish. All right, now, let's fast forward about a week to March the 28th. Ooh, at 11:12. That's kind of like noon. And the first quarter moon is rising. Because at noon, the sun's going to be high in the sky, and you're going to work your way backward to the eastern horizon, a quarter, and that's going to be the first quarter moon. It's going to be rising noonish. And look at that azimuth up there, in between 50 and 55. Let's give that an azimuth of, 53 or something. How about that? Okay? Boom! The moonrise shifted dramatically on the horizon in just a week. And then the next phase I wanted to do is a full moon. Oh, look! 19, 12, 13, 14, 15, 16, 17, 18, like 7:20. The full moon is rising there. But our clock shifted. So that whole telling time by the moon thing is great for the equinox, but then you get into the real specifics of it, and you're like, plus or minus 2 hours, how about? But still, the azimuth is what I'm interested in. 90, how about 6 or something? 96? Yeah? Boom, let's put that full moon all the way back to here. So the moon shifts up, shifts back, and now, in the night, we got that third quarter moon rising, and I'm looking at that azimuth 30, call it 1 or something. Boom, 31 is all the way down there, 131, and that would be the third quarter moon. And remember that right when I started on the vernal equinox. I started on March the 21st, and it just so happened that was also a new moon. And that new moon, then what would the sun be doing though? Like as we go into the summer, the sun would be setting more in the northeast. And then the sun, after the summer, would come back in the fall to the east again. And then in the winter, the sun. So that's following the same path as the sun is, right? We just kind of pick up with the sun on the new moon, and then we do in a month what the sun would do in a year. Okay. Now, here, very interestingly, is the next new moon on April the 19th. And if we looked at that azimuth, I'm saying, you know, between 80 and 85, maybe call it 83 or something. Ooh, from the new moon at the March 21st date to the next new moon, you're doing that thing with the sun, but guess what the sun is also doing? Moving. And the sun had a month to make its slower progress up into the northeast, and the new moon rises with the sun. So when the moon is back to where it was on the horizon, that takes 27.3 days, the sidereal period of the moon. But when the moon comes back to being new again, that takes that extra 29.5 days. Yeah, you follow me? You with me? We're going to get to the end. We're going to get all the way to the end. And so this is a little table of moonrise positions. And the summertime, though, is something I want you to think about. In the summer solstice, the sun is going to rise in the northeast. And so is the new moon. But then the first quarter moon is going to move back to the east, to the southeast at a full moon, and then back to that third or quarter moon in the east. The moon is going to do that sun cycle, but it's always going to be starting from wherever the sun is, and the sun keeps moving too. All right, what do you want to take away? Like the sun, the moon's rise and set positions, they move across the horizon over the course of a month. All right, should we do it? Last part, part 7, yeah? The major and the minor lunar standstills. All right. Now, something I already showed you. The sun, for us at 42 latitude, 65-degree angle between the extremes. All right, that was something I already showed you, but I don't expect anybody to remember 65 degrees. I certainly didn't. I had to put it up there for myself. All right, and then I turned the diagram. How could the moon's rise? Dang it, dang it. The sun is only sweeping through 65 degrees at the extremes, but the moon, the numbers that I just picked off those diagrams, is sweeping through 78 degrees. How could the moon's rise and set limits lie beyond those of the sun? Because the sun did that thing because of the Earth's tilt. And the Earth's tilt, it causes the sun's cycle, and the tilt hasn't changed. So what's up with the moon going more extreme than the sun goes?
Well, the moon's orbit is tilted with respect to the equator of the Earth.
Boom, there it is. The moon's orbit is tilted with respect to the, fancy word, ecliptic, which is the plane of the sun and the Earth. The Earth goes around the sun on a plane, and that we call the ecliptic, and the moon's orbit is tilted at 5 degrees. Now, this is also why we don't have eclipses every time we have a new moon and full moon, because there's that tilt, and it puts that moon out of the eclipse position, potentially. Potentially. All right, now, here's a little chart that I found back from 2021. And from 2021, you could see that we kind of got these. What is the blue line? The blue line is the moon on the angle from due south. So essentially, that's like the azimuth. The moon is swinging back and forth on the horizon, back and forth. The sun takes a whole year to do that. But if you did some numbers right now, it, according to this 2021 data, 55 degrees, 125 degrees. Could you do the difference between those? Between 125 and 55 would be like 70? Yeah? 70? But what I just showed you was that just now, this is now like 2 years later, we're already doing 78-degree swings. So the swings of the moon are increasing over the last 2 years. And the reason why is because not only is the moon's orbit tilted, but that tilt is doing this over 18.6 years.
Epicycle motion?
So it's, what do we got? The regression of the nodes is often what it's called. And the nodes being the spot where the moon's tilted plane crosses the ecliptic, the plane where the Earth goes around the sun. And so only when the moon is in those nodes can we have an eclipse, which is why it's rare. But in addition, you've got this plane of the moon wobbling. But guess what? Let me slow it down. One of these wobbles takes 18.6 years. And so in one extreme, what you can get is the wobbling of that moon to be more extreme than the ecliptic from what we call the celestial equator. I'm getting a little advanced because I'm at the end of the talk. But it's more extreme. We call this the major standstill. That's what I just showed you in the data. It's going out farther than the sun goes. But on the and that's coming up. January 29th, 2025 is like officially the max. But you can already see that today as I'm showing you. It's on its way. It takes 18.6 years. It's like there's no rush. All right? But if you got to look at the next couple of years, or eventually it's going to kind of keep going back. And on the other extreme, you put that tilt, that wobble, you wobble it inside of the ecliptic with respect to that celestial equator, and now the moon is inside of those extremes of the sun. That's not as exciting. It's kind of more exciting when it's out further, get more extreme, but it can be inside. And this right here then is like 19 years worth of data where you can see the sun doing its thing year by year, but the moon, right, much more often, and really wobbling itself out more extreme and less extreme with that peak in 2025, January of 2025. So what's kind of cool is then you get this, horizon diagram. You're looking north, south, east, west. You're looking at the summer, the solstice sunrises and sets. They're special events. But then these moon rises and sets are also special when they're even more extreme. And people have potentially, right? There's a lot of debate and controversy over these things, but I just threw this in here because I think it's fascinating that a lot of people argue that a lot of these ancient monuments, like Stonehenge, for example, have alignments that are not just for the sun, but they're also for the moon's long-term cycles. And that you can set up your giant rocks to indicate those different directions where those extremes of the moon that go beyond the sun and those minimums of the moon that lie within it. So this summer, what I'm going to be looking out for, all right, final thought here, is that this summer, the sun is going to be setting in its extreme, right, June 21st. Now, the new moon rises with the sun. Can't see that. But what would be fun to observe is a full moon. And that means that the full moon is going to be opposite the sun in the southeast rising, setting in the southwest. But it's going to be even further into the south than the sun would be, which means it's going to make this tiny little appearance and it's going to set back down. It's going to be really low to the horizon, more low than it will be in, right? This for the next two, maybe three, well, these 2 years leading into 2025 and then the 2 years after, it's going to be more extreme than it will be at any other point in the cycle. And that's something that I'm going to look forward to looking for this summer. That really low moon. And it looks huge, and it's going to just be there on that horizon around the summer solstice. Do you remember anything tonight? Dawn, yeah? Dawn, like in Goodnight Gorilla. That's the dawn right there. And then to finish, right? We'll sing you a good night song, a little poem that I like to sing to my kids that I found in this book called The Rain Babies. First off, thanks for coming out tonight. I really appreciate it. You were a great audience. But bye, 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 bye. The moon is half a lemon pie. The mice who stole the other half have scattered star crumbs in the sky. Bye, 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 bye. My darling baby, don't you cry. The moon is still above the hill, and soft clouds gather in the sky. Hey, thank you.
Check out the hang time on that applause. That was great. Thank you. So, do we have any questions? In the back.
Is the moon's orbit around the Earth always like an equal distance from the Earth, or is it elliptical?
It is elliptical. So everything is, I mentioned earlier in this talk, right? Everything is more complicated. So I did a lot tonight, and I really appreciate all your attention throughout. But as far as we went, you could go farther, which is that the moon gets closer and farther away. And so you'll see in the news from time to time a supermoon, right? If you're familiar with that, the supermoon, it just means that the moon is a place in its orbit where it's closer, and so it's actually slightly bigger in appearance in the sky. That elliptical orbit is a complicating factor on all the stuff that I taught you tonight, but it's like, as you want to master the major stuff first, and then eventually, you can add in those more and more fine-tuning of everything.
When there's going to be a supermoon? How can you tell when there's
I look like you look it up. Yeah?
And why is it that the moon sometimes appears larger
So this is a hotly debated topic. And the answer that I will go with is that it is a perceptual phenomenon. It's that you seem to think it is, but if you get out your instrumentation and make some detailed measurements, there's no difference. Now, there is slight differences because of that elliptical orbit, as you said. Sometimes it's a little closer, sometimes it's a little far away. There are measurable differences in the size of the moon, but it appears bigger when it's on the horizon because your eye zooms in and it has something to compare it to. When it's up there in the vastness of the sky, there's nothing to compare it to, and you just feel like it looks smaller.
If I could just sort of jump on here, you talked about the elliptical orbit. When there are solar eclipses, there are sometimes what we call annular eclipse. And so what people are saying is that, you know, in this elliptical thing, when the moon is at what we call apogee, in other words, it's furthest away from the Earth, if an eclipse happens then, you actually will see what we call the ring of fire, that the moon does not completely cover the sun. And so you get this nice ring of light that just is, you know, because the moon just can't completely cover it. Then you get a super moon, or when as it's closer in its orbit to the Earth, we call that perigee. Then it completely covers the Earth, and so I believe there's an annular eclipse happening sometime this year, in October. By the way, next year, 2024, Kopernik will actually be celebrating its 50th anniversary. We're having a number of events throughout the year. I've arranged for a solar eclipse to happen in 2024. It will happen. It's April 8th at about 2:45 in the afternoon. It's a Monday during the school year. Back in 2017, we had about 1,500 people up here. Probably won't have quite that many, but we do have the solar glasses that we'll give for your admission. And but anyway, I just wanted to sort of jump in on that. And
If you go about 2.5 hours west of here.
you could avoid the crowds and to come here.
It won't be total.
But it won't be. Yeah, we'll be about 98% covered here, but it won't be full. You have to go to Syracuse. Totality is actually in the center of the. Actually in Buffalo. Yeah. So, any other questions here in the room? Because do we have any questions on? All right. So we've had a nice. We do have a question. Hold on. Let's jump over here.
If you would be able to, could you go back to the slide where it shows the azimuth progression for the moon and the sun over 18? Yeah, no, you passed it.
I'm sorry.
The progression. It looks like there are small cycles that happen roughly a couple times a year. Did you?
Yeah, so this is like I think I'm not sure, but there are these other, I forget the name, there's a fancy name, and I was just reading about this, and I'm not even sure if what I'm thinking of is those little wiggles, right? But there is a little wiggle that I think was first attributed to Tycho Brahe, who noticed it, who observed it, that those little wiggles are due to the fact that the sun's gravity is different when the moon is in its orbit close to the sun versus farther away. And so it causes an additional little wiggle. And this has a fancy name that won't come to me because I don't really understand this fully. And it's like it was at the edge of where I got to, right? But that's an additional factor with the it's an ellipse. And then this extra little wiggle, right? All these are extra factors on top of everything that I told you. The perturbation, yeah. There's another word too that goes with that, yeah, but it's a perturbation due to that difference in gravity of the sun. I mean, that seems like it, yeah? Those little, I see them, right? I see what you're talking, right? Is that the perturbation? I don't know.
And it looks like it almost has not quite a 2-cycle perturbation within a year. If I'm looking at sort of the peak
Right.
to the peak, if that's June of 2016, 2017, so twice a year we seem to have those. Interesting. Okay, so we need you all to start studying this more and come back and explain this.
Hey, thank you all very much. You've been a great crowd.
Right.
Thanks for everybody online. Have a good night. Happy St. Patty's Day.
All right. So, again, what we do here is, if you did pay and we didn't get a chance to actually do any night viewing, you can go to the cash register and get a card to come back on another night. For those who are here for the first time, if you'd like, we will actually give you a tour of the observatory. You'll be able to see the telescopes. You just can't see through them. So we'll start that tour in about 5 minutes out in the lobby.
Thanks for coming. I hope you enjoyed it.